Welcome to the Ruckus Associate Smart Zone Administrator demonstration series for the SmartZone OS 5 release. In this series of demonstrations, we'll show you the functionality of SmartZone OS 5 along with the basic configuration of many aspects of the controller. SmartZone OS 5 is the network controller operating system that's available on the SmartZone 100 and SmartZone 300 hardware platforms, and as we'll be discussing here, the virtual SmartZone network controller platform. This presentation describes the advanced options of zone configuration. This presentation is the second part of the zone configuration presentation series. If you've not already viewed part 1, SmartZone Zone Configuration, please view that presentation before watching this one. So let's jump right into it. Most of the settings in the advanced options of zone configuration relate to the behavior of access point radios. So we're just going to go through a quick summary of some of the most important settings in here, what they do and how they affect operation of the radios on the WLANs that exist within the access points that are part of this zone. So first is the auto channel selection. This sets how channels will auto adjust to RF problems in the environment. So there are basically two options available for the auto channel selection. We have the background scanning or channel fly. So background scanning is a process of having the access point temporarily go off channel in order to gather information on the surrounding WLAN environment and then return. So background scanning is the default. It runs every 20 seconds unless you configure it otherwise with the options right here. The data recorded during the background scanning is used for radio channel and power adjustment. It's also used for rogue access point detection and access point location detection. With background scanning enabled, auto channel selection provides the option to use the data from background scanning to adjust the channel setting to optimize the WLAN's operations. Let's take a quick look at this. Background scanning is a relatively simple operation and service, and it operates like this. So an access point operates on a set channel, and then the access point scans alternative channels and then records data. Then the access point returns the original channel, and the access point scans the next channel and records data, and the access point returns to the original channel. Background scanning is invisible to the client stations who continue to operate on the access point's normal channel or the one that they've been told to operate on. Now if we change this to channel fly, the operation behaves a little bit differently. Channel fly changes the channel periodically and then records the performance data on that channel. The data recorded is used to determine the channel that offers the best potential throughput, and then the metrics gained from channel fly can be used by auto channel selection. So let's take a quick look at how channel fly operates. Channel fly does this by regularly changing the access point to a new channel by following a process like this. So the access point operates on a set channel, and then the channel is switched and announced in a beacon to all the clients. So all the clients change channels with the access point. And on regular intervals, the access point will move to a new channel, and the channel switch will be announced in a beacon, and everyone will move with it. And this will go on as the access point moves to a new channel. Now the important thing to keep in mind is that when using channel fly is background scanning is still being performed. The choice is only which of these two methods you're going to use to provide metrics for auto channel selection. So you can use either background scanning to determine which channel is best for auto channel selection, or you can use channel fly. And also keep in mind that channel fly can take some time to effectively analyze the environment, and it's not suitable everywhere. So if you want to utilize channel fly, you should ensure you leave enough time for the system to settle and that you monitor network performance to ensure that the client experience is not affected adversely by the change. The channel change frequency allows you to determine how often channel fly will change a channel to gather these metrics. It's a range from more often at 100 minutes to less often at 1440 minutes or 24 hours to change channels and gather the metrics. It's important to note that the selection of background scanning or channel fly is unique per radio. So the 2.4 gigahertz radios can use background scanning or channel fly independent of the setting for the 5 gigahertz channels. Now the background scan options are both configurable whether or not background scanning is chosen for auto channel selection. That's because, again, background scanning is used for multiple purposes, including rogue access point detection and access point location detection. So we have options to configure those here for how often we're going to run that background scan on each radio. So we can adjust each radio independently with a range of 1 to 65,535 seconds, and the default being 20 seconds. Bonjour fencing is a feature designed to limit Apple's multicast DNS or MDNS service discovery. Once it's enabled, if no rules exist, you can set up a policy right here by clicking on the plus, and the plus will open up a dialog and allow you to configure a bonjour fencing policy. Now, bonjour fencing and the somewhat related topic of bonjour gateways are somewhat advanced in their specialist subjects. We are going to have another demonstration in this series that covers both bonjour fencing and bonjour gateways, so take a look for that module if this is a feature you're interested in using. Now, Smart Monitor, which is disabled by default, allows WLAN services to be shut down if the access point loses its connection to its default gateway. So we have some configurable threshold values. If we turn this on, we can configure an interval for how often we perform a health check for that default gateway, and then the number of retries before we consider that gateway to be failed. So in this case, it would take 3 failed checks on 10-second intervals, so 30 seconds before we would see the WLAN service disabled because the default gateway is inaccessible by the AP. Next, we have the AP ping latency interval, and this measures the latency between the controller and the access point, and then it sends this data to a northbound data streaming destination like Ruckus's Smart Cell Insight or SCI solution. And next is the AP Management VLAN, and this is used to set the default VLAN for management traffic. We can use whatever the AP setting is, or we can force a particular VLAN to be used for management on the AP by selecting this box and putting the VLAN that we want this traffic to be sent on. Rogue access points are access points in the area that are not managed by the controller, and background scanning will detect them when gathering data on channel use and access points in the surrounding areas. If rogue AP detection is enabled, a classification policy can be configured with several variables to identify rogues. There's a default policy that's provided that will identify a few elements for us. So let's take a look at that. So we'll select the default policy, click the pencil to edit it. The default policy has 3 rules that will identify APs as malicious. These are if they're advertising the same networks, doing MAC spoofing, or SSID spoofing. And then there's an ad hoc rule to identify rogue APs. When this is enabled, any rogue access points that are detected can be found under Report and Rogue Access Points. They'll be listed there as either rogue or malicious APs, and most of the time a rogue will simply be a neighboring access point. Any listed as malicious will also be given a reason for that classification. And in addition to that, if you have maps and you have geographic coordinates for all of your APs, you can select the Locate Rogue button and show where that rogue device was detected. Now you also have the option to enable these events and alarms for all rogue devices, or just enable events and alarms for only malicious rogue devices. So you'll have that option for you. The next option here, to protect the network from malicious rogue access points, if you turn that on, what's going to happen is that you'll now allow the access point to take action against perceived threats. So how this works is that the access point will identify clients that are attempting to associate to the malicious rogue AP, and then the access point, our access point, will send a deauthenticate to the client, so sending a deauth frame that will appear to have been sent from the malicious rogue. Now you need to note that this can cause some unintended consequences, and in some countries it might actually even be illegal. So it's recommended that this option is not enabled without extensive knowledge of WLAN security practices and rules of the operating environment. Next is client load balancing, which, as the name implies, balances clients across different access points. So it kind of works like this. When joining a WLAN, a client will naturally attempt to connect to an access point that appears to have the strongest signal. With client load balancing enabled, the favored access point does not allow the connection, and the client connects instead to an alternative access point. There are configurable thresholds that are used to determine the SNR, or signal to noise ratio, of an adjacent AP before load balancing will be applied. Client load balancing is disabled by default and is reliant on a few things for it to operate. It requires background scanning. Once enabled, it can be disabled on a per WLAN basis, and it's disabled if you enable another feature called client admission control. So like with many of the settings we've talked about already in these system settings, it's recommended you leave the default settings in place unless you do some extensive testing and analysis on the network to determine how this is going to impact operations. Next, we have band balancing, and this one balances the client load across the access point radios. So band balancing shouldn't be confused with band steering. Now, many modern devices will now look to connect on a channel that offers the greatest throughput. So with 802.11n and 802.11ac, devices are able to use 40 megahertz and 80 megahertz channels in the 5 gigahertz range, so they naturally favor 5 gigahertz. So band balancing will force some of these devices to roll back to 2.4 gigahertz instead. And this is all based on radio activity. So you can use a slider over here to control associated stations to meet certain band distribution requirements that allow us to perform some dynamic band balancing. So if you move it to disable, it disables band balancing. Basic says during heavy load conditions, the operation withholds probe and authentication responses in order to balance the clients. In proactive, it uses the basic configuration in addition to actively rebalancing clients using the 802.11v BSS transmission management, or BTM. And then strict uses the proactive configuration in addition to forcefully rebalancing clients using 802.11 BTM. Band balancing is enabled by default and it can be disabled per WLAN, but it's typically best to just leave this at the default settings. Now we move on to client admission control. This is used to allow or deny new client connections based on the available quality of experience, or QoE, for currently connected clients. When client admission control is enabled, access points use algorithms based on configurable settings in order to permit or deny client connections. Use of this feature, though, disables client load balancing and band balancing. And because of this, if client admission control is enabled on a zone, you'll get a message that pops up letting you know what the impact's going to be and if you really want to enable it. So we'll just say no here and continue on. So next is the protection mode, which allows you to set the mode in which a 2.4 gigahertz radio will use to reduce collisions. The default is RTS-CTS, and in most instances, this setting should be left at the default value. Now the AP reboot timeout reboots the access point if the access point detects a loss of connectivity. The access point will reboot if it can't reach the default gateway after 30 minutes, or if the AP can't reach the controller after 2 hours. You can disable this by setting the timers to 0. So 0 means never reboot, or up to 24 hours. So these are the options available for both the AP reboot if it cannot reach the gateway and if it cannot reach the controller. And the timing you use should be set according to your redundancy strategy and your WLAN settings and requirements. The Recovery SSID option allows you to disable the broadcasting of the recovery, or what's known as the island SSID, in Ruckus access points. The default setting for the Recovery SSID is to be enabled, so if you do not want APs to advertise this recovery ID in the event of a problem, you can disable that here. And finally, we have the Directed Multicast options. Directed Multicast transfers multicast traffic as unicast packets to enhance the performance of the wireless network. And this only affects traffic going into the wireless network. There's no change to the multicast traffic if the destination port is the wired Ethernet port. So we have three options to control multicast conversion from actual multicast to being sent as unicast packets. So the option to multicast traffic from wired clients enables multicast to unicast conversion from wired clients to a non-trunk interface. The wireless option enables multicast to unicast conversion from wireless clients, and network enables multicast to unicast conversion from wired clients on a trunk interface. Now this concludes the SmartZone configuration presentation for the advanced option of zone configuration. This is the second part of a two-part series on zone configuration on SmartZone OS 5. So hopefully you viewed both of these, and hopefully the information that was provided in them was helpful to you, and you'll come back to more presentations in this series in the future. Thank you.